In one of the harshest regions on Earth, where winter temperatures can plunge below -30 degrees Celsius, and Siberian windstorms are powerful enough to cripple industrial machinery, China has created an unprecedented engineering marvel, mobilizing 10,000 workers to cut through a massive frozen river and construct a $500 million ice megacity that exists for only 30 days. This is not only a technical battle against the limits of nature, but also an ambitious effort to revive the frozen frontier into a new strategic industrial hub of Northeast Asia. So how were Chinese engineers able to extract, preserve, and assemble millions of gigantic ice blocks to create the largest illuminated ice wonder on the planet? Join Terran Works as we explore the story behind this extraordinary achievement. China did not build this $500 million wonder to last forever. They built it to completely disappear. Deep within northeast China, where the temperature difference between summer and winter can reach nearly 80 degrees Celsius, Harbin possesses something almost nowhere else on Earth can offer. An entire 1,900-kilometer river transformed into a natural material mine that appears for free every year. However, the greatest challenge is not extracting the ice, but the very nature of the material itself. Unlike concrete or steel, ice constantly cracks under vibration, deforms with temperature changes, and begins melting the moment it is removed from the river surface. That turns the entire project into a direct race against time and climate, almost completely defying the logic of modern construction. But if this extreme limitation can be conquered, Harbin would not only become one of the world's largest winter tourism hubs, but also a driving force behind the revival of Northeast China's industrial region within the country's broader strategy for global competitiveness. In other words, this is proof of how the nation transforms a land of extreme climate into nearly limitless potential. That is why every year, Harbin must launch an almost absurd operation, cutting through the massive Songhua River and constructing an entire glowing megacity in just around 30 days before spring begins destroying everything. And to understand how Chinese engineers are able to accomplish this, we must begin with the very first step, cutting through the meter-thick ice of the Songhua River. Around early December each year, when temperatures in Harbin plunge deep below freezing and the ice on the Songhua River reaches nearly 1 meter thick, one of the strangest extraction operations on Earth officially begins. Before the ice cutting starts, engineering teams must continuously survey the river's thickness to identify areas capable of supporting heavy machinery weighing dozens of tons. The entire river surface is then marked with standardized cutting grids to divide it into tens of thousands of uniform ice blocks. What makes Songhua River ice different from ordinary artificial ice is its higher density, lower air bubble content, and purity level reaching up to 99%, allowing LED light to pass through the entire structure at night. At this stage, high-powered industrial saws carve long trenches through the nearly 1 meter thick ice layer. Once the industrial cuts are completed, workers use long steel chisels to break the connected ice underneath and control the separation direction of each block. In sub-zero temperatures, a single crack in the wrong position can render an entire half-ton ice block unusable. Each massive ice block is separated from the river surface using steel hooks and specialized mechanical systems before being pulled upward. The entire process must happen extremely quickly before fractures begin spreading through the ice structure. After being detached from the lower ice layer, each block is connected to a mechanized rail pulling system that slides it directly from the water surface onto the frozen river above. This method reduces vibration and distributes force more evenly compared to lifting the blocks vertically with cranes, minimizing the risk of cracking in large ice sections. Harbin Ice and Snow World requires more than 400,000 cubic meters of ice and snow every year to construct structures spread across approximately 1.2 million square meters, equivalent to nearly 170 standard football fields. At this scale, ice extraction resembles a massive quarry operation, far more than a winter festival. Every day, more than 2,000 ice blocks weighing nearly 500 kilograms each are continuously cut over several weeks, transforming the entire Songhua River into a gigantic industrial construction site, operating almost non-stop under extreme temperatures. But extracting the ice is only the beginning. The real challenge is figuring out how to transport and store tens of thousands of gigantic ice blocks for months before they begin to melt. After the classification process, thousands of ice blocks weighing hundreds of kilograms each are continuously transported by forklifts and heavy-duty trucks between the Songhua River and the massive central construction site. But transportation only solves half the problem. Harbin must accomplish something even more absurd, finding a way to store tens of thousands of tons of ice for several months. To achieve this, the ice blocks are moved to enormous outdoor storage areas, where they are stacked into massive layers resembling industrial shipping containers. To slow the melting process, the blocks are arranged in large stacks and covered with multiple layers of insulating materials, such as straw, fiber mats, and specialized industrial thermal coverings. This system reduces the rate of heat exchange with the surrounding environment and keeps the ice core temperature stable over long periods of time. What makes this extraordinary is that the entire logistics system exists solely to extend the lifespan of a material that is already destroying itself day by day. The most common misconception among visitors is believing that the structures in Harbin are built entirely from solid ice blocks. But in reality, behind those massive towers lies an entire complex steel framework functioning as the invisible skeleton of the entire city. The first construction teams begin by building temporary foundations and securing steel columns directly into the ice layer and the frozen ground beneath it. After that, thousands of steel modules are continuously assembled to create a structural system capable of resisting torsion, vibration, and the powerful winds of the Siberian winter. The greatest challenge emerges once the structures begin exceeding dozens of meters in height, as the weight of the ice blocks themselves generates enormous pressure on the framework below. At the same time, constantly fluctuating temperatures between day and night cause the ice to continuously expand and contract. Despite this level of complexity, the entire steel framework across an area of 1.2 million square meters must be completed in only around 15 days. And once the final steel skeleton is completed, the most complex phase truly begins, constructing gigantic, illuminated ice towers before spring arrives to destroy everything. After 10 months of storage, Harbin enters the most critical phase of its entire logistics system, moving tens of thousands of tons of ice from the Songhua River to the massive central construction site. At the outdoor storage yards, workers must first remove the natural insulation layers that had been used for weeks to slow the melting process. Once the ice blocks are fully exposed, industrial forklifts begin separating each block from the gigantic container-like stacks before loading them onto heavy-duty trucks. As a result, thanks to a massive cold storage system and strict temperature control procedures, the ice melt rate remained at only around 10% throughout 10 months of storage. And as the final transport convoys begin entering the center of the construction site, Harbin moves into the most complex stage of the entire project, constructing gigantic ice towers. This is no longer ordinary ice sculpting, but a true mega-engineering project where the limits of material, climate, and time are all pushed to the extreme simultaneously. Once the steel framework is completed, industrial cranes begin lifting ice blocks, weighing hundreds of kilograms, to heights of dozens of meters. Workers positioned above must then precisely trim each block directly at the installation point to ensure nearly zero margin of error before securing them to the structure below. What makes Harbin especially unique is that it almost never uses cement or chemical adhesives to join the ice blocks together. Instead, workers use water as a form of natural glue. When poured into the joints under deep sub-zero temperatures, the water freezes almost instantly and becomes the bonding layer that merges the ice blocks into a single gigantic structure. But this is also what makes the entire construction process extraordinarily brutal. At -30 degrees Celsius, combined with constant Siberian winds, metal surfaces can freeze directly onto equipment, while the human body loses heat rapidly enough that precise movement becomes far more difficult after hours of continuous work. After the central ice towers are completed, Harbin moves into another massive phase of construction, building a giant ice slide system stretching more than 500 meters. But at this scale, the slides are no longer just a winter attraction. If the slope is too steep, velocity can exceed safe limits within seconds. But if surface friction becomes too high or the turning curves lack stability, the entire experience can lose control and dramatically increase the risk of high-speed collisions. That is why, before the final ice layer is applied, Harbin must first construct a dense, compacted snow foundation to stabilize the entire slide route. Workers then continuously add multiple thick layers of ice above it to create a surface that is hard enough, uniform enough, and smooth enough to minimize vibration while riders move at high speed. Throughout this entire process, hundreds of thousands of multicolored LED lighting systems are installed deep inside the ice blocks, transforming the entire city into a gigantic illuminated architectural network. Every day, the slide surfaces must be continuously inspected, resurfaced, and adjusted to ensure that thousands of visitors can use them safely under constantly changing temperature conditions. If ice is used for structure and illumination, then snow is what defines the entire visual language of Harbin. It is the material used to create gigantic castles, towering sculptures dozens of meters high, and fantasy structures stretching across the entire park. The snow is first compressed under massive pressure to form high-density blocks stable enough for large-scale construction. Artists and workers then use saws, shovels, and specialized cutting tools to continuously remove excess material until the final forms gradually emerge. In essence, snow sculpting is not a process of adding material, but a process of removing material to reveal the structure hidden inside the massive snow block. From simple white snow blocks, Harbin gradually creates an entire fantasy architectural world in the middle of the Siberian winter, where the ice structures represent engineering capability, while the gigantic snow sculptures transform extreme climate into a form of urban-scale artistic language. Unfortunately, only a few weeks after reaching its most spectacular moment, rising temperatures begin causing the giant wonders to lose structural integrity, while the entire lighting network that once transformed Harbin into a glowing city in the Siberian winter gradually disappears as well. However, what makes this extraordinary is that despite existing for only a very short period of time, Harbin Ice and Snow World has still become one of the largest winter economic engines on Earth. During the 2024 to 2025 winter season alone, Harbin welcomed more than 90 million visitors and generated over 137 billion yuan in tourism revenue, equivalent to nearly $19 billion US. And perhaps the most remarkable thing is not that Harbin can survive within ice and snow, but that humanity has learned how to transform winter itself into an industry. So what do you think? Is building an entire $500 million city only to watch it melt away the greatest waste in history, or the pinnacle of modern engineering capability? China's response did not begin with science. It began with organized desperation. In the early years, saplings were carried into the desert and planted almost blindly into open sand. Pits were filled in by wind within hours. Roots dried out before they could anchor. Survival rates were so low that failure was not a risk, it was the expectation. Season after season, millions of trees died, buried, uprooted, or burned by heat within weeks of planting. Yet the planting continued. At this scale, failure was not a reason to stop. It was treated as data. Every dead tree marked a boundary of what could not work. By the early 1990s, the strategy reversed. Rather than confronting the desert head-on with trees, planners shifted focus to a more basic task, slowing the movement of sand itself. Grasses were introduced before forests, low-growing, resilient species capable of binding sand and weakening wind at ground level. Across moving dunes, millions of straw checkerboard grids were laid down like rough stitches across an open wound. They did not remove the sand. They merely stopped it from moving. Wind velocity dropped near the surface. Moisture lingered for hours longer, then days. For the first time in decades, the sand remained still long enough for life to attempt a return. With surface movement restrained, the real battle shifted underground. Soil hydrodynamics became the decisive front. Researchers realized the core problem was not how many trees were planted, but how their root systems competed for the same scarce water. Root depth was recalculated. Spacing between plants was increased to prevent multiple trees from drawing from a single groundwater pocket. Soil structure was modified to reduce evaporation, preserving thin layers of moisture between cycles of heat and wind. Species were selected not for rapid growth or visual density, but for their ability to endure multi-year drought cycles without collapse. These adjustments were subtle, almost invisible, but they compounded. By the early 2000s, survival rates, once unthinkable, exceeded 80% in certain zones. Forest belts expanded. Sandstorms that once engulfed cities weakened or disappeared. From an engineering perspective, the system worked. For a brief moment, it seemed as if everything was over. Satellite images showed an unbroken band of green. Winds slowed, sandstorms disappeared. On paper, the system had succeeded. Then the dry years arrived. No catastrophe, no headlines. Rainfall dropped just enough to matter. But underground, the balance began to slip. Groundwater recharge slowed. Trees that had survived for years began to weaken. The signs were hard to see. To outsiders, the forest still stood. Researchers understood. The system had reached its limit. Every new hectare of green increased water demand. The desert no longer failed through sandstorms. Quietly, it failed through hydrology. In Moose, success no longer meant moving forward. It meant avoiding collapse. It was at this moment of apparent success that a deeper contradiction emerged. The landscape was stable, but not free. What existed was not a self-sustaining ecosystem, but a carefully designed and continuously managed system. Technical success had been achieved. Ecological independence, the ability of the system to persist without constant human intervention, remained unresolved. Across the world, humans have attempted similar interventions with mixed results. In Africa's Sahel region, the Great Green Wall was designed to halt desertification through a restored land corridor stretching across the continent. Despite decades of effort, progress has remained uneven. Political instability, funding shortages, and water scarcity have constrained long-term success. Israel took a different path. Rather than greening the desert at scale, it optimized water use. Precision irrigation, wastewater recycling, and crop selection allowed agriculture to exist without attempting to transform the entire landscape. Productivity increased, but the desert remained a desert. In the United States, the lesson came earlier and in a more painful form. After the Dust Bowl of the 1930s, the federal government launched the Great Plains Shelter Belt Project, planting more than 200 million trees as windbreaks stretching from Texas to North Dakota. The project reduced soil erosion and dust storms for decades. But as subsidies declined, land returned to private ownership, and agricultural pressure intensified. Many shelter belts were removed or deteriorated. When centralized management weakened, the system quickly lost its capacity to withstand stress. Moose is different, not because deserts in China operate differently, but because governance capacity is different. The ability to mobilize labor, enforce land use restrictions, subsidize long-term maintenance, and absorb ecological risk is rare. The lesson here is uncomfortable. China's success in combating desertification may depend less on ecological science, and more on whether a political system can stand outside market logic and electoral cycles long enough to sustain intervention. How do you assess this claim? Share your perspective in the comments below. The positive impacts are measurable and significant. Forest coverage in some regions increased from under 2% in the 1950s to over 30% by 2020. Sandstorm days dropped from more than 100 per year to fewer than 10. Agricultural yields increased nearly tenfold. Household incomes rose from subsistence levels to tens of thousands of yuan annually. Cities stabilized. Infrastructure survived. Migration slowed. But beneath these gains lie new dependencies. Many restored areas rely on monoculture tree species, limiting biodiversity and increasing vulnerability to disease. Increased vegetation alters groundwater dynamics, sometimes depleting aquifers elsewhere. Changes in rainfall patterns benefited some crops while harming others. The system became productive, but also more tightly coupled to human management. Remove the maintenance, and the balance begins to unravel. What satellite images largely fail to show is water. Every tree that survives in moose operates within a strictly limited water budget. Even without irrigation, vegetation draws moisture from soils and shallow aquifers, meaning total water demand rises as green cover expands. The paradox is that restoration's success alters the very hydrological balance that allowed it to begin. In semi-arid systems, groundwater recharge is slow. Just a few dry years can erase decades of gradual recovery. The system does not collapse suddenly. It weakens over time, often unnoticed until it is too late. In moose, restoration is therefore not a reversal of desert conditions, but a continuous negotiation with water. When that balance shifts, even slightly, the desert does not need to advance aggressively. It only requires humans to misjudge how fragile the system has become. Muse reveals an uncomfortable truth. Green does not always mean recovery. Satellite images can show forests, but they cannot show what matters most, whether an ecosystem can stand on its own. A child who grows up independent does not need to be held forever. A forest is no different. Only when it can support itself has it truly recovered. And a desert that stops moving has not necessarily lost the forces that drive its destruction. In moose, humans did not eliminate the forces behind desertification. They merely held them in check. The wind is still there. The soil remains poor. Water is still scarce. What changed was the presence of a management system strong enough to constantly adjust, correct, and prevent the landscape from slipping past a critical threshold. This is the structural vulnerability of engineered ecosystems. They can withstand natural forces, but they are fragile in the face of human disengagement. Moose shows not only what humans are capable of building, but also what cannot be allowed to be abandoned. The green line holds until it doesn't. From orbit, the Moose Desert looks conquered, but deserts do not surrender. They wait. Beneath every stabilized dune lies sand that remembers how to move. Beneath every tree lies a water balance that can shift. China has shown what is possible when human systems are aligned at scale. But the future of moose depends not on trees alone, but on whether this green line can be maintained for generations. The final question is not whether humans can turn deserts green. It is whether they can afford to keep them that way.